Howdy folks, Mr. Reed here, and welcome to one more question. So what I'm going to be taking a look at right now is the general behavior properties of exponential functions. So exponential functions are really useful. They can be used to model a number of important things in the real world. So it's good to have an understanding of them, especially if you're kind of going that calculus route. There's a lot of neat properties that they have that end up being especially kind of interesting once you get into calculus. So in the meantime, exponential functions, what are they? You're in the right place. Mild video, I guess. Let's get to it. Okay, so exponential functions. First of all, let's look at the form that they'd have algebraically. So for an exponential function, we're talking about something that is y is equal to some constant base to the power of a variable exponent. This is a base exponential function with no transformations being done. So that's what I want to explore right now. Anyway, now that base is kind of peculiar because it behaves really nicely under certain circumstances. So for instance, just to kind of throw some stuff out there. If I had 2 to the power of x, you can imagine that 2 to the power of different things is a fairly normal thing to evaluate. So 2 to the power of 2, that's going to be fine, so it's 4. 2 to the power of 3, great, that's fine too. 2 to the power of negative 2 would also be fine. So that is going to be the reciprocal, and so you get 1/2 now squared would be 1/4, or you could square it first. The order actually doesn't matter. You could square it first and then do the reciprocal afterwards. So either of those would be fine. Now, I'm not going to get too much into the case of what would happen if you had an irrational exponent, but if we had something that was, for instance, -3/4, that's about as busy as I'll talk about right now. So that would be reciprocal, so you'd get 1/2, and then we could take that and raise it to the power of 3, which would be 1/8, and then we'd be looking for a number that, when multiplied by itself 4 times, would give us 1/8. So the 4th root is another way to say that. So there is a nice way to describe that numerically for us right now from what we should already know at this point before getting into exponential functions. Of course, as I said, things that are represented irrationally, they're going to actually show that this way of thinking about exponential functions is actually it's convenient for especially for those of us that don't have some sort of basis in logarithms and limits and series at this point. It really is the nicest way to talk about them. So to avoid getting any deeper than I need to for that, I'm going to leave it at that. So 2 to the power of those things, it's fairly straightforward. That's good. What if I had -3 to the power of those things? Well, -3 to the squared, that's nice. That's just going to give me 9. -3 to the power of like 3, it would be -27. That's going to be fine too. What about -3 to the power of -2? Well, that's okay too. So I'm going to have basically squared. This is going to give me 9, and then the reciprocal, so 1/9. Awesome. So what about -3 to the power of -3/4? So we get the negative, that's fine, so it's the reciprocal, and then the power of 3 is going to be 27, so it's -1/27. But then we're looking at the 4th root, so something when multiplied by itself 4 times gives us -1/27. If that thing were positive, multiplying by itself 4 times is going to give us a positive, because positive times positive times positive times positive is a positive value. What if we were to instead have this thing be a negative? Well, it's going to be a negative times a negative times a negative times a negative. Positive. Oh, that's positive too. That's awkward because we're supposed to make the value -1/27. So what that ends up meaning is that there is actually no real number that can represent -3 to the power of -3/4. Now, that's not to say we couldn't get into something complex numbers with some imaginary number stuff, and that might be a ticket to be able to answer this in a different way. But for the time being, we are working in the real number system, so that thing is a no-go, which means we are going to give certain limitations to our C value. We're going to make C values have to be positive. 0 is a bit awkward. It's not to say it wouldn't be something you could evaluate for different things, but it's not really an exponential type behavior anyway, so we're going to say c greater than 0. And actually, more than that, if you had a c value of 1, that's not really going to do a whole lot either. So it's kind of an awkward thing to say it's an exponential function because it acts more like a linear function. So we're going to break things up into two categories. We're going to go and say that there are c values that are between 0 and 1 that might be interesting to look at, and we're going to have c values that are greater than 1 that also might be interesting to look at. So let's take a value that is between 0 and 1. Let's take probably the simplest one to evaluate, which would be 1/2. So if I said we have a c value of 1/2 and we're looking at y is equal to c to the power of x, how is that going to behave? Well, if we had an x value here of 1, let me actually put it in a table form. So if I have x versus c to the x, then we'd have x value of 1 is going to give us 1/2. X value of 2 would give me 1/4. If I went back the other way with a 0, that's going to be a 1. And if I were to put in like a -1, I would be able to get a 2 for a value there. That's kind of cool. So if I were to plot some of those values, let's say that this is a 1, and then we get a 1/2 at 1 and maybe a 1/4 at 2. So it seems to kind of go down like this. And it's going to keep getting smaller and smaller, but it's never going to actually hit 0. So that actually has a property of having an asymptote, we say. So it's going to exhibit a behavior that becomes so close to a particular type of function that we can't really say that there's any difference between the two, other than we know it's not equal. So it will never be 0. It will be like 1/4, then 1/8, then 1/16, then 1/32, etc. But it's never going to be just 0. It's going to be 1 over some really huge number. So that follows along a line that's going to become basically y is equal to 0, and it's going to continue out that way. So I would say that this has a horizontal asymptote of y is equal to 0. If I go in the other direction with the negative exponents, I said that 1/2 to the value, to the power of -1 was going to be the reciprocal, so it would be 2. And so it would be up here somewhere. And then it would end up being like 4 and then 8. So it's going to start growing really fast, and it's going to go up the other way. So we have an exponential function that kind of looks like that. If I were to look at c that is greater than 1, let me just actually reset things a little bit here and clean it up. So we'd have c is equal to, I don't know, I'm going to just pick something. No, I'm going to go 2. The smaller the number, the better for me. So we'll go with 2 and say that x versus c to the power of x would look something like this. I'm going to actually start at -2 this time. So if I had a c of 2 to the power of -2, we'd get 1/4. -1 would be 1/2. 0 would be 1. 1 would be 2. And 2 would be 4. So we end up getting, again, very similar values, which will be more apparent once you kind of explore what's going on here a little bit more with exponential functions. But for the time being, if I were to take this and want to graph it, so what we would do is I'm just going to do some really rough sketching here. So that's at 0, 1, let's say, 1, 2, 2, 4, and then backwards, -1, 1/2, and then 1/4 for 2. So it's going to look basically the same as last time, but this one's growing. The other one is actually decaying, and we would see if we had them graphed on the same axes that these are actually going to be reflections of each other. So sorry for my amazing ability to sketch. You kind of know what the general shape is going on there. I hope you do anyway, so my apologies for that. So the idea there is we should have something that's roughly a horizontal reflection, or not roughly, exactly a horizontal reflection of each other. So one of them is what we call exponential growth. That would be the c value that's greater than 1. If you have a c value that's between 0 and 1, that's going to be experiencing instead exponential decay. This is, of course, if you're looking as x values increase, which is going to be the typical thing to do. So as the x values increase, one of these functions grows and one of these functions shrinks or decays. So that's kind of the base look of what an exponential function looks like. What an exponential function does is actually something pretty incredible. So what you should do to experience what exponential growth is like is come up with a fairly simple pattern that you want to follow for a little while. For instance, one of the things I use in my class is a little story, and I'm going to modify it a little bit, so if my students are ending up listening to it, they'll hear something a little bit different, but it's basically the same thing. If you are a young person, probably too late by the time you're learning this in high school, but if you have little brothers and sisters, you could try to get them to trick your parent or guardian pretty easily with the following. So let's say there's a chore they want you to do daily. Make your bed. Let's just say that's something that is a little bit of a place of contention, and at this point there's an impasse. So convince your younger brother or sister to say the following: I will make my bed if you give me 1 penny the first day I do it, 2 pennies the second day I do it, 4 pennies the third day I do it, etc. until the end of the month. And at the end of the month, if you're still paying me the money and I'm still making my bed, then I'll just go on making it for free for the rest of the year, or whatever the case may be. So that's all well and good, but let's think about the implications of that. So on the first day, you are saying that what you're going to be paid is 2 to the power of 0. Now, that's a little bit weird that I put it that way, but it makes more sense when you understand that the next day, I'm using a base of 2 because I'm doubling what it was that I was getting on the first day. So that's 2 to the power of 1. If I were to double again, that's 2 to the power of 2. If I were to double again, that's 2 to the power of 3. If I start on the first of the month and it is the shortest month possible, 28 days, would mean I end up getting to 2 to the power of 27 by the end of that first, I guess, month. Best case scenario, I'm getting up to 2 to the power of 30. Now, what I'm going to do is suggest that you pause the video, grab a calculator, and assess those two values. If you don't think this is a good deal for a small child trying to, I don't know, bait their parents into a really bad situation, it is, because those are very, very large numbers that started off very, very reasonable. 1, double it. 2, double it. 4, double it. 8, double it, etc. Doubling is a very, very strong idea. Actually, I don't remember who the quote is attributed to, but from playing Civilization, oddly enough, one of the quotes that comes up is that the power of compound interest is one of the greatest forces or strongest forces in the world. I don't know exactly what the quote was or who it is attributed to, but the idea of compound interest is something that's tied in very closely to the exponential function. Actually, all compound interest problems can be related to this idea of exponential functions. And it's really interesting to see how much growth there is. Actually, there is so much growth associated with these particular functions that you can actually take a power function of any exponent and put it up against a growth exponential function. So it has to be greater than 1 of any size. And eventually there will be an x value. So where this one is actually greater than this one, which is pretty incredible. It does not early on. So actually, there's a little bit of funky stuff that goes on at the very, very beginning, because if you use an x of 1, it's also true that the point 1.001 is greater than 1 to the power of 999. But if you use an x value of 2, two is a really bad example. There's going to be a huge gap in between them, with the power function being the one that's winning at that point. But it's actually true that the exponential function will overtake it and will be the one that's growing faster eventually. If you keep on keeping on and you're going with the root of calculus, try to remember that for when you are down the road in learning something about L'Hopital's rule. L'Hopital's rule, and maybe if I can remember, I'll put a link to that somewhere in this video when months down the road I get to making my L'Hopital's rule video. And if you're doing L'Hopital's rule, you can actually show that the limit as x approaches infinity of this function over this function, if we were to continually take derivatives of these two things together, we could show that the one that is the exponential function is going to win. And so it's pretty nifty, pretty cool stuff. Long story short, there's a few things about exponential functions you should kind of understand. So it's growth function if the c value is greater than 0. It's a decay function if the value of c is between 0 and 1. Those growth and decay functions are really just horizontal reflections of each other, which is pretty neat. They always go through 0, 1 if they're not transformed. I don't think I even mentioned that earlier, but you might have noticed that yourself. That is a true statement. The domain for both of them is XER. The range for both of them is y greater than 0. When I say both, I mean the growth and the decay. And oddly enough, we can't use c values that are negative, as we experienced earlier. They are super fast growing. Of course, if they're decaying, that means they're also super fast decaying, where they go down to a very low value quickly, and then they basically become as close to nothing as you could ever be. All right, so I blabbed on for probably way too long for that one, but I hope you learned some things about exponential growth and decay functions. Generally, y is equal to c to the power of x is what we're talking about, and they're really useful, so I hope you like them. If you like this video, like, subscribe, and as always, take care, folks.